Thank you very much. Thank you for being here, Professor Tsitsika. It's always a pleasure. Of course, the title should have a question mark, but it depends on the point of view. For us dealing with clinical data and precision medicine, it's without a question mark. For the applications in total, it is with a question mark. So mainly the main problem is two different classification. One is how we deal exactly with artificial intelligence. So what is the real meaning, the real tool, how it was built, and what it means to people, to humanity. And the second thing is in which sort of application it is involved. Okay, I will try to tell you both. So it was 2018 when I met Sophia. Sophia is the robot that you see in Switzerland, and it was in the panel of speakers together with me. It was 4 speakers, like we do here. Yes. She had a human interpreter. So any questions addressed to her were passing through a human, a person that was changing slightly the questions in order that she could understand them and provide answers. After this translation, the answers were 100% correct and very intelligent, sort of speaking. When it finished, it was open for the audience to address questions without an interpretation. So she could not say a correct answer to any questions that were coming from children. This was very impressive. Yes, no correct answer. From our point of view, knowing informatics tools, mathematics, and all that inside, and being in bioinformatics, the bioinformatics fields from the day that started, and it's not so old, it's 2004. And I will tell you why. What I was saying, it was not something that was having intelligence. It was not machine learning, not artificial intelligence, not robot thinking, and all that. It was a huge database with questions and answers that can be processed in real time. This is very, very different of what we are thinking of artificial intelligence. The terminology comes from 1960. 1960, informatics was not even there. Informatics that we are talking about. So people was having the license to put the terminology he wanted and dream. Okay, so artificial intelligence, perceptrons, all that collapsed in the first 20 years because there was no computational power. Okay. The first 2 victories, that's why you can see all the question marks, if it is intelligence or adaptation, deep understanding, lots of data, thinking of or training. The main question here also is that the data that artificial intelligence uses in the databases are getting all the time better and better. Why that? Because we provide them. What we do is we provide very, very good data for machine learning, for artificial intelligence. It's the humanity that does this. And also, you can see the features AI does and does not. It's not really able for quality thinking from the scratch. Innovation is something that you cannot find there. Yet we have 2 big victories of AI and bioinformatics. The first one is the Human Genome Project that ended up with, started at 1919 from Professor Adonarakis in Geneva, a genetist. He was not mathematics, he was not dealing in informatics, he knew nothing, but he knew the correct procedure that we could map the genome for us. This was a huge win in 2006. We are talking of very recent advantages. We're talking for things that we have all experienced, and we have them experienced in a very intense way. The thing also is that no one from us could believe in 2000, not even Antonarakis, that only 5 years after there will be so huge computational power. This was the first shock that we had. And the second shock is that we could have access to it from our labs. This also was very strange. So what we believed is that, we really could adjust all the things that we do, all our activities, under this new framework. And this did work. The second victory of AI is a few days ago. We have the Nobel of Physics and Chemistry given to people that created AI tools from protein folding. What is protein folding? And sorry for that, but it's very important to understand it. What was very important, and we had worked in a lot of time, was protein misfolding. Protein misfolding, how a protein is not well folded, it directly connects to almost any new disease mechanism that exists in the human body. This has been done from the medicine around 50 years ago. No one could find it. So finding the way of how a protein is well folded was the holy grail for the genetists, but no one can solve it. I have personally met perhaps hundreds of people that have dedicated their lives in biology labs, 30 years, 40 years, with no real result. When we started in our lab to deal with that, we also got a huge research project for that is ending next year with detection of protein misfolding. We did not think that we could touch the protein folding problem. We could not think that this could be done. So we rejected as our research activity, and all the lab was focused on protein misfolding. Okay, and we had some good results. 3 days ago, half of the Nobel Prize was for an application that called Rosetta. Baker did it, and he could build correct proteins from the scratch, AI application. And this is and now it's been already being used in pharmacology companies, not labs. And the second one, it was 2 persons from Amazon, I think, that they could create AlphaFold 2, the way that not only you have the final results, but all the mechanisms besides work or do not work. This is the protein misfolding problem. And all this with AI. So is AI working in high performance computing? Yes, it works. It works very, very good. This is what we were thinking from the beginning, and I will tell you what also we have achieved in our labs. It worked very good. Why it is working very good? Because it's a black box for you that can always be better. It cannot be worse, or it cannot do wrong things on its involvement. Why is that? Because it's based on thousands of data that always are are improved, used, or thrown out. Okay. So what we have done ourselves, we used AI for making digital biobanks. This was the first announcement of AI digital biobanks in the world, and we have announced it last year in our lab. And also, this was dealing with digital data coming from clinical data that have involved in 10 completely different disease mechanisms. It was cancer, it was autism, it was PTSD, it was neurodegenerative diseases, but exactly the tool and the infrastructure and the interoperability was the same for all of them. This was the crazy thing. So you can have the same infrastructure, digital data coming from clinical data that can work together. You can have horizontal or vertical queries, and you can have biobanks with AI tools that can connect them one to each other. So the fuel of this AI innovation for having these things getting better is exactly this, is the big data. Big data and good data and clean data. Clinical data is having exactly this very good characteristic because they are coming after clinical trials, they are coming after very serious and careful studies concerning human diseases. Yes, it's okay, 5 minutes. Okay. What is the main problem? But I will get back to you with that later. So the main thing, which is exactly what we see, is that the mathematics were there, the algorithms were there, computational power was not there, 2005 only. But what didn't exist, and this was a very problem, is the data. The data is something that we start feeling about it a few decades ago, yet with a wrong way of working with them. Is AI dependent of human thought? Is it dependent of quality processes? Is it dependent of mathematics? It's go along in very big steps in high performance computing by itself? Of course not. This is something that we are saying all the time. The people saying it's completely stupid. AI is made from human, and when something different come up, this is exactly what we are told in AlphaFold 2 and Rosetta, did not came by itself. AI did not have a way of improving it and solving the folding problems of protein. People did it with names and they took the Nobel. Okay. So I won't bother you with the concepts that are behind, but I can tell you what really is AI doing in nowadays, and this is extremely important, is precision medicine. Precision medicine is the core of the change in the medicine that we will see in the next decade that will be applied to all of us. We will see it happening to our children, for sure, and if we are lucky, also to all of us. What is this? This is that the disease mechanism, without knowing the biological backup, what is really is doing in the biological problem, and this is what Baker solved. AI can produce the profiles of the human, of the persons that have the disease. So you can have different profiles with exact therapeutics matching without even knowing deeply the biological mechanism that goes along. This is crazy, but it's true, it's happening. It's here. This is a small example of the change. We had, see the numbers, 710,000 clinical trials. 2,700 of them only had AI tools, but they are the ones that we use for the future. So eventually everything will turn there. I won't say the good things. Let's stop a little in the dangers and the problems. If we have an overview, we can say very lightly that there are three different applications of AI. One is the one that I have shown you. AI used in the hands of experienced researchers in high performance computing. I think we have no problem there. The second one is AI, the problems that you are dealing, AI in use for basic human abilities. So coming down before the abilities are developed. This is crazy. This is very dangerous. The third one is a new incorporation of AI tools in enhancing abilities that are missing in human. This is the third thing is something that we will try to have a conference next week, Genesis, and we are building a team for starting working on that. I think we don't know exactly what will happen, but this is very interesting. Okay. Thank you very much.